We're going to review an old exam I gave in a face-to-face class of 1430. So to begin with, you're going to see the formulas that I gave my students on the exam. I do recommend that these formulas make their way onto your 3x5 note card. All right, so the first question we see is a question involving understanding how to interpret a graph based on our new calculus topics. So we have the following graph of a function f of x. The first thing we're asked to do is find some limits if they exist. If the limit does not exist, write DNE for does not exist. And be careful, some are one-sided limits. So first, let's go ahead and identify that our first limit is x going to -4 from the left-hand side. So if we come up to our graph, right here is x equals -4. If we approach along the graph x equals -4, we can see that we are approaching the value y equals 4. So our limit would be 4. The second limit is also a one-sided limit. We have the limit as x goes to -4 from the positive side. So now we're going to look at x equals 4 from the positive side. If we come along from the positive side and we move along the graph towards x equals -4, we're again going to get the value of y equals 4. Now, since the left and the right side limits are the same, that tells us that the limit without a side associated to it, the general limit that is, also exists and is equal to the same value, in this case 4. The next limits are also a left and right side limit, followed by a general limit. We're looking towards x going to 5. So here we have x equals 5. If we start and we look along the left-hand side of the graph, we can see that we are approaching a y value of -2. However, if we approach 5 from the right-hand side, we see that there is no point there, but that's okay. The limit only cares about the value that you approach, and we're approaching a y value of +1. Now, since our left and our right side limits are not the same number, -2 and 1, that tells us that the general limit as x approaches 5 does not exist. Okay, the next are a few quick limits that we can do. Notice the following 3 limits are all general limits. As x approaches -6, well, right here is x equals -6, we can see that we approach a y value of -2. If x is 0, we're right at the origin, and we approach a y value of -4. And if x is going towards 2, here's x equals 2. Now, we notice that when x is equal to 2, we have an open point on our graph, but that's okay. The limit doesn't care what the function value is. It only cares if you approach the same value from the left and the right. And in this case, we do. We approach the same value of y equals -2. So the second part of this question is to list all the values of x where the function is not continuous and briefly explain. Now, the first place we notice, or should notice, that the graph is not continuous as we read from left to right is when we run into our first hole in the graph. And that occurs when x is equal to 2. And at x equals 2, we already found that although, this was the very last limit that we did, although the limit as x goes to 2 of f of x exists, and we know it exists because above we found the value was -2, in fact, f of 2 itself does not exist. And hopefully you remember, in order to be continuous, both the limit has to exist, the function value has to exist, and they must be the same value. The second place our graph is not continuous is when we see the jump in the graph, and that occurs when x is equal to 5. And when x is equal to 5, unfortunately, the limit as x goes to 5 of f of x does not exist. You'll notice the function value does exist. The function value f of 5 is -2. But the limit doesn't exist, and so we are not continuous. The last part of this question, I'm going to have to move the graph in a moment out of our sight, so let's just read it to start with. List all values of x where the function is not differentiable, and for each, briefly explain. So we know that a function is not differentiable for two different reasons. The first reason is that the function is not continuous. If it's not continuous, then it cannot be differentiable. So we know that that will happen at x equals 2 and x equals 5. We just found that in part B. However, the other place a function is not differentiable is where it comes to a point, or in math, what we call a sharp turn. It may not be a solid or a sharp point, but it will be some sort of turn in the graph. And that occurs when x is equal to -4. The reason for this, remember when we're talking about the word differentiable, that means a derivative exists. And the derivative is the slope of a function at a given point. Well, if we were looking at the left side of the point on the graph when x is equal to -4, our tangent line would look like this, meaning that our derivative would have a positive value because the slope would be positive. However, if we looked at the right side, we would see a tangent line that looks like this, which means the derivative would be negative because the slope of our tangent line is negative. So as you read in the textbook, this is the reason that we are not differentiable at sharp turns. The derivative cannot exist because the slope of the tangent line would be a different sign. So let's go ahead and we'll formally write that up. So we know that x is not going to be differentiable at x equals 2 and x equals 5. And the reason is the function is not continuous. And we already determined above why it's not continuous at these two values. The third place we're not differentiable is at x equals -4. And our reasoning here is just that we have a sharp turn in the function, or you could say the graph of the function. So in the next video, we're going to look at another problem on the exam, problem 2.